So up until now, whenever we've talked about a series, we're typically talking about the entries being concrete numbers. We're talking about adding up 1 plus zero point 0.1 plus zero point zero 0.01, etc. Um, but what we're doing now is rather than concrete numbers, we're going to be adding up polynomials or adding up functions, and we're going to be combining these functions and seeing what happens. So this first example we're going to be talking about, we're taking the sum from n equals 0 to infinity of x to the n. And so writing this out, we get, well, x to the 0 is 1, x to the 1 is x. We get the following pattern of 1 plus x squared plus x cubed plus x to the fourth, etc. And so the question is, as this goes off to infinity, as we include infinitely many terms on this, what is the function that we get? And sort of before we can answer that, we have to ask, does this even make sense as a function? If for a specific x value, when you plug x into this 1 plus x squared plus x cubed expression, if that thing diverges, if that's some infinitely large, infinitely big thing, then maybe this function doesn't even make sense when talking about that x value. For example, if we plugged 2 into this, and we're adding up 1 plus 2 plus 4 plus 8, etc., as the number of terms in this list goes to infinity, this ends up being infinity, like this gets infinitely big. So in a sense, it doesn't even make sense to talk about this as a function for the value x equals 2. For other values, however, this might end up converging. For values less than 1, this thing you may recognize as the geometric series. This thing ends up equaling 1 over 1 minus x. But remember, this only works when x, the magnitude of x, is less than 1. So we want to approach this thing in a slightly different way. Let's say we forgot about all of this geometric series stuff, and all we had to work with was this first series. We want to know for what interval, for what values of x, does this whole thing, does this series make sense as a function? In other words, what are the values of x for which this series converges? So that's the main question in this section. For what values of x does this thing converge? Okay, so there's a bunch of different tests that we can use, and we actually so oftentimes could use any of them. The one that actually is going to be the most useful to us is the ratio test. So in case, oh, what happened there? Okay. In case you don't remember it, the ratio test says that, all right, to determine if a series converges or not, we're going to calculate this limit. And it's the limit of the ratio of the next term over the current term. Okay, so let's take a look at this expression. If we want to do the ratio test for this series, and remember, up until now, we've done ratio tests for concrete numbers. Now we're doing them with variables in there, but all the rules are still the same. So we want to apply the ratio test to the sum, to the series n equals 0 to infinity, x to the n. Well, in order to do this, we need to calculate this expression. Well, so we want to know what the limits as n goes to infinity of the n plus 1th term. Well, we're going to plug in n plus 1 over the nth term And we're going to include absolute values. Doesn't make a difference on this particular example, but it sometimes does. Well, x to the n plus 1 over x to the n. Oh, actually, so never mind. It does make a difference on this example, but we can go from there. Well, this ends up being just x. And what the ratio test says is, depending on what L is, our series is either going to converge or diverge, or if it so if it's less than 1 or greater than 1, and if it's equal to 1, it actually doesn't tell us anything. So if we want to know for what values of x does the series converge, we are basically asking for what values of x is this limit. So this thing is the L from up there. For what values of x is L less than 1? Well, if L is x, then it's just when x is less than 1. And again, we've got absolute values, so this ends up being the absolute value of x is less than 1. So for x less than 1, the series converges. All right. So this actually gives us the radius of convergence. It gives us all of the values of x where it makes sense to think of this series as a function. Okay. One last thing I want to show. All right, here, change screen. All right. Okay, so this is that function we were talking about. So we said a minute ago that this 1 plus x squared, etc., using our geometric series knowledge, ends up being 1 over 1 minus x. And that's what the dotted line function is here. 1 over 1 minus x looks a lot like 1 over x. It's just shifted a little bit. Okay, so the idea is that on the interval between -1 and 1, so on this blue interval, the series 1 plus x squared, etc., does a reasonable job of approximating what's going on. So let's look at the first few. These actually end up being the partial sums, the first two approximations of this series. In other words, let's just take the first few terms of this infinite sum. So if we only take the first term, our g of x is a constant function, the constant function 1. If we allow for a first degree polynomial, as in a linear term, 1 plus x, this is 1 plus x squared. You might notice this is written a little bit differently. The 2's end up canceling. This is 1 plus x squared. You can also notice that, at least on this blue region, we're getting closer to approximating what's actually going on. So this red line does better than the previous red line. And then the third degree does even better. So these distances are getting closer and closer. So as we allow this to increase more and more, this approximation is getting closer and closer to what's actually going on, at least on the blue interval. You might notice that for x that's less than 1, this actually ends up keeps switching back and forth, right? So we're not doing a good job at all of explaining what's happening for things less than -1. And that's because if we plugged in a -1 into here, this thing actually ends up diverging as we include higher and higher degree polynomials. The same type of thing happens for values bigger than 1. Back when we were pretty low, we had some values that were bigger than 1 that still showed up in this picture. As we increase the degree of the polynomial, these values are actually going to get really, really big, really, really fast. So we're adding together, if we plugged in 2 for this example, it's 1 plus 2 plus 2 squared. All right, that's manageable. When it's also plus 2 cubed plus 2 to the 4th plus 2 to the 5th, all the way up to like a 20th term, this thing is just sky high. It's nowhere near what it's supposed to be, which ends up being actually a negative number. Anyway, the point of this is, one, the interval for which this series converges, this function, the series of polynomials, looks a lot like the function that it limits towards. And as we make this a series, as we add up infinitely many of these, this actually ends up equaling the function in question, at least on the interval between -1 and 1.